Okay. I guess we're all here now, just about. I don't have my attendance sheet with me right now. It's in my house. I'm not at home right now. Again, apologies for canceling the last class. I had been ill. I am presently recovering. I am in much better shape right now, and I think we can do okay. I haven't graded your papers yet because of my illness. I hope to do it over the weekend. Okay, so let me take control of the screen and let's talk. Oops. Let me get back here. Zoom. Okay. So I had pre-recorded for you the last time. By the way, if there are any questions, just please ask. A short lecture on the correlation coefficient. And there's not too much to say about it. We showed that it was equal to the covariance divided by the product of the variances. And we showed that it's always a number between -1 and it's a much more useful expression than the covariance, because the covariance can run from -infinity to infinity, whereas the correlation coefficient takes on these finite range from -1 to 1, which is very nice. Moreover, for values close to 1, if rho is near 1, then x and y are linearly are related. Linearly related. If it's near 0, then not linearly related. And this is more important probably in statistics than it is in actual probability theory. But it's a very, very useful measure. Now that we, and in computing rho of xy, it's done the same way. When you want to compute your rho of xy, what you have to do first, of course, is you have to compute sigma of xy, which remember was e of xy minus e of x times e of y. And then, of course, sigma sub x. And similarly for sigma sub y. So it's really pretty easy. You look at these tables of the probability distributions, you can compute sigma sub xy pretty easily, and you can compute the correlation coefficient. And I gave some homework problems involved on that. And if there's a difficulty, we'll talk about it and we'll work 1 or 2 out. Today, though, I want to talk about a really neat idea, the moment generating function. And we'll just call it the MGF. So let's talk a little bit about this. We've already talked about moments. We defined the mean to be the first moment. Now, for convenience now, we're going to define a general moment to be, this will be called the kth moment. Actually, the kth moment about the mean. Now, so the special case, of course, is mu is mu1. And in general, mu sub k for a discrete random variable, which is e to the x of k, will just be the sum I'm sorry, I did that wrong. Let's rewrite that. Oops, come on, Warren. And I'll illustrate this soon enough. Now, in a couple of examples, for example, we know how to find e of x squared. How do you find e of x squared? You just take the summation x of I squared times p of x of I over all possible I values. And that's important because if you know e of x squared and you know e of x, you can find the variance. Well, I want to define now the moment generating function. Okay, so given the random variable x, we define the moment generating function denoted by to equal to e to the t x power okay. I'm assuming, of course, that this expectation exists. Okay, you'll see in the text, I assume there's some value k on which this converges. This is called the moment generating function. Now, what's nice about this moment generating function is I'm going to show you in a moment that this will generate all moments, and it will give us a very convenient way of finding the mean and the variance for lots of different distributions. Now, that's pretty significant. And the reason for that is normally, especially when we get to the calculus portion in the next chapter, to find the mean and the variance, you're going to have to integrate. In the discrete case, we use sums, but we're going to see that integration can sometimes be messy, and this will save us a lot of hard work. Okay, so let's talk a little bit about this. Well, before I proceed, I want to tell you a result from calculus. We all are familiar with the exponential function. Now, we can show in calculus, usually we show this in calculus too, that e to the w power is equal to 1 plus w squared over 2 factorial plus w cubed over 3 factorial, and so on. And that's true for all w. This can be proven in calculus too. I'm not going to prove it now. Now, why is this useful? Well, by the way, sometimes we'll just write it this way. That's the same result using sigma notation. Now, let me show you why this is useful. Let's suppose we replace w with t times x. Then e to the tx becomes 1 plus tx plus tx squared over 2 factorial, and so on, where e to the tx is equal to 1 plus tx plus x squared over 2 factorial t squared, and so on. Now, suppose I take Remember, this is defined to be e of e to the tx, the expected value of e to the tx. So this becomes e of 1 plus tx plus, oh, I'm sorry, I lost, plus t squared, x squared over 2 factorial, and so on. So this becomes, using the properties of expected value, e of 1, which is 1, plus t times e of x, plus t squared over 2 factorial e of x squared, plus t cubed over 3 factorial e of x cubed, and so on. Or m sub x of t is equal to 1 plus, now, this, of course, is mu. This is mu2. The next one will be mu3, the third mean. So I've just shown that the moment generating function is equal to 1 plus mu t plus mu2 t squared over 2 factorial, and so on. Now, I want to make some observations about this. So notice the coefficients are exactly exactly the what do I call it? The moments. Now, the first thing to observe is when t is equal to 0, the moment generating function is always equal to 1. If that didn't happen, you made a mistake. The next thing to observe is if I take the derivative with respect to t of the moment generating function, what do I get? I get mu plus 2 mu2 t over 2 factorial plus 3 mu3. And notice, if I evaluate this at 0, I get the mean. Which means the derivative of the moment generating function is always the mean. If I take the derivative again, I end up with, that's a constant, I end up with mu2 plus 6 mu3 t over 3 factorial, and so on. And then notice the second derivative at 0 is equal to mu2. So let me just show you what I've just shown. Okay. So I've just proven the following. I've just proven, given the moment generating function, okay, the mean is equal to the derivative evaluated at 0, and mu2, which is equal to e of x squared, is equal to second derivative at 0. In fact, want to prove in general, if you follow this through, that the nth derivative at 0 is equal to the nth moment. We don't really need them. These are the two key results. Just look what this now says. This now says if you want to find the mean is just equal to the moment generating function evaluated at 0, and v of x equal to the mean minus e of x squared, but that's equal to m double prime of 0. So let me summarize what I just said. So we've just proven the following very important fact. If we have the moment generating function is the mean of the distribution, e of x squared, therefore v of x is equal to m prime at 0 minus m sub x double prime of 0 squared. Oh, this is wrong. This is e of x squared. Wait a second. So v of x therefore is equal to e of x squared minus the mean squared, or m double prime of 0 e of x squared minus mu squared. Now, let me note that m of t is nothing more than e to the t x of I, p of x of I in a discrete case. So let me look at an example for you to illustrate what's happening here. Let's suppose we have the following probability distribution. P of x of I say 0.2, 0.3, 0.4, 0.1. Now, of course, we could find the mean the old way, but let's just illustrate let's find the moment generating function. It's going to be summation e to the t x of I times p of x of I over all possible values. So this would be e to the 1t times 0.2 plus e to the 2t times 0.3 plus e to the 3t times 0.4 plus e to the 4t times 0.1. So m of t, the moment generating function for this particular distribution, just turns out to be 0.2, I'm sorry, this is a t, 0.2 e to the t something's wrong here. No, we're good. Plus 0.3 e to the 2t plus 0.4 e to the 3t plus 0.1 e to the 4t. Now make some observations. Firstly, notice m of 0 is 1. Remember, e to the 0 power is 1. If I take the derivative, let me remind you that the derivative of e to a to the t is a e to the at. That's from calculus 1. So if I take the derivative of m prime of t, what do I get? I get 0.2 e to the t plus 0.3 e to the 2t times 2 plus 0.4 e to the 3t times 3 plus 0.1 e to the 4t times 4, or that gives me m prime of t, the derivative of the moment generating function, turns out to be 0.2 e to the t plus 0.6 e to the 2t plus 1.2 e to the 3t plus, what's the last one? This is a 4, wait a second. This was a 4 plus 4 e to the 0.4 e to the 4t. And now notice, if I compute this at 0, I end up with just, what do I get? 2.4? Which tells me the mean of this distribution, which I could have gotten the old way, of course, is 2.4. If I take the second derivative, we end up with 0.2 e to the t plus 1.2 e to the 2t plus 3.6 e to the 3t plus 1.6 e to the 4t. And the second derivative at 0 just turns out to be whatever it turns out to be. What do I get? I get 3.6 and 1.6 is 5.2, 5.4, 6.4, 6.4. Is that 6.6? Yeah. 6.6. So the variance is 6.6 minus 2.4 squared, which turns out to be 0.84. So the point is, we can always find the variance and the mean from the moment generating function, okay? So the moment generating function determines all moments, which implies we can find the mean and the variance. And by the way, in statistics, they talk about the third moments and the fourth moments. I talk about it in the exercises. They're really not too important for us, but one can talk about higher moments as well. Okay, if this were the only reason we wanted a moment generating function, we would be wasting our time. But we're going to see that it's extremely useful in many, many situations. And there are at least two important results that are going to be very, very valuable for us. Computing the moment generating function is really very straightforward. It's basically a plug-in exercise. You have to excuse me, I'm feeling a little woozy still. Okay, So there are two key results or three key results about moment generating functions that we're going to need a lot. So let's suppose the following. Let's suppose x1, x2, up through x sub n are independent random variables. And let's suppose they each have moment generating function with mx1 of t, mx2 of t. So each of these n random variables, which is independent, has its own moment generating function. Let capital X be the sum of all these random variables. So I have these n independent random variables and each have their own moment generating function. Then the theorem says that the moment generating function of the sum is the product of the individual moment generating functions. That's an interesting and powerful result. And the proof of that is really very simple. Let me walk you through it. And we're going to use it a lot in the next chapter or two. So X is defined to be x1 plus up through x sub n. The moment generating function is e to the tx so that becomes e to the t x1 plus x2 plus x sub n. Now I'm going to use in a moment, remember any function of independent random variables is independent. I'm going to use that in a moment. If I use the property of the exponential now, e to t of x sub n, I distribute it. And now since they're independent, this is the product of the individual exponentials. X. And that's equal to m1, the product of the moment generating functions. And you're going to see, for example, in the next section, we're going to look at different distributions. We'll look at a binomial distribution, maybe a Poisson distribution. And when they're independent, if we want to find the joint, if we want to find the expected value or the moment generating function, all we have to do is multiply them together because they're independent. So that's one key result about the moment generating function. And by the way, this has a name. This is called the reproductive property. Now, we're going to actually find closed form expressions for moment generating functions. So this is going to be very, very useful for us down the road. Next result. Linear change of variables. So let's suppose x has moment generating function m sub x of t. So I'm giving you some random variable. I'm telling you it's moment generating function. And then I let y equal to ax plus b. So the question is, how is the moment generating function of y related to the moment generating function of x? So e of t, I'm sorry, e of ty is equal to e of okay. Now we use our properties. This gives me e to the a. E to the a t x plus b t. I can rewrite this as e to the bt times e to the t ax. I'm just rewriting this now. This is a constant, so this is e to the bt. And now this is just a moment generating function of m sub, what's the notation I use in the text? Rewrite this as e to the a t x. So m sub y of t is just equal to e to the bt times m sub x of at. So this says if you make a linear change of variables, the moment generating function of y is related to the one of x, this exponential factor out in front, and you take t and you multiply it by a. We'll illustrate that with an example soon enough. Now, one last result about the moment generating function, and this is rather difficult to prove at this level. The moment generating function uniquely determines the random variable. What do I mean by that? It means given any random variable, it has a unique moment generating function. And given that is for this course at least. And given any moment generating function, there's a unique random variable that has that. That needs to be qualified in a more advanced course about something about a set of measures 0, which we're not going to worry about in this course. So the moment generating function uniquely determines the random variable and conversely. So if you know one, you know the other. Anybody have any questions so far? So let me sort of sum up what I just talked about, okay? So we defined the moment generating function. Its definition is e to the t x, where x is the random variable. In the discrete case, it's easy enough to compute. We know the first derivative of the moment generating function is the mean. The second derivative of the moment generating function is e of x squared, which means sigma squared of x is equal to n double prime of 0 minus n prime of 0 squared. We know if x1, x2, x of n are independent, and x is equal to their sum, then the moment generating function of x is the product of the moment generating functions. And those are the key results for the moment generating function. So the first part of your homework assignment will be this section, section 2.11. Is this 2.11? Yeah, 2.11. So please work out those exercises. Some later on may be a little tricky. Don't worry about the tricky ones. So now let me tell you what's happening. Okay, we're almost ready to finish chapter 2. But this last section, chapter 2, is a rather large one, and it considers some very important discrete distributions, which you may have learned about in some of your other courses. So we'll give them a pretty complete treatment, I think, and we'll use the moment generating function to make life much simpler for us. Okay, so let me begin with the binomial distribution. And I'll just talk briefly about the binomial. That's probably one of the more important ones. So let me define a binomial distribution. I'm going to use the notation I'm using in the text. I was very careful about. So I want to define the random variable x. It's said to be a binomial distribution if it has the following three properties. Every time you perform the experiment, remember the experiment could be tossing a pair of dice, flipping a coin. Every time you do it, we call it a trial. Each trial or each event, each trial is independent. Two, I can classify each trial as a success or failure. And the probability of success or failure on each trial is the same. Any experiment that has these three properties Let me give you an example. I toss a coin, a fair coin. Every time I toss the coin, I either get a head or a tail, and they're independent events. I can call a head success. I can call a tail failure. And if it's a fair coin, the probability of success every time I toss a coin is a half. Or I toss a pair of dice. I can call success getting a sum of 6. Everything else can be failure. So those are two examples of a binomial distribution. Okay. So let's introduce some notation. Suppose X is a binomial distribution. I'll let N equal the number of trials. And let's let P equal to the probability of success. And Q will be the probability of failure. Okay? So here's a typical problem, okay? And by the way, so, all right. Let's suppose, so the question is, here's a problem we want to solve. What's the probability that there are K successes? That's a typical problem. Well, what's the probability that there are at least K successes? Or in most K successes? So what we want to do is for the binomial distribution, we want to develop a simple result, but let me introduce some notation. I want to observe that for binomial distribution, well, to designate that this is a binomial distribution, I might say it's a binomial distribution. I'm looking for K successes from N attempts and trials, and the probability of success is P. So this is just another notation showing that the answer depends upon, well, one, it's binomial. K is the number of successes. This is the number of trials. And P, of course, is the probability of success. So, for example, suppose a coin is tossed 10 times. The probability of a head is 0.6. Determine the probability of 5 heads. Well, this is clearly a binomial distribution. The number of times I'm tossing this coin is 10. The probability of success of getting a head is 0.6. And we want to know what's the probability of getting exactly 5 heads. That's the question. Well, using the notation I just indicated, I could represent the answer this way. This would represent the answer. So the question is, how do you figure this out? Is there a simple way of figuring this out? And the answer is yes, of course there is, and I'll show you in a moment. Anybody have any question about the problem I just posed? So this is a typical example of a binomial distribution. Again, how do you recognize a binomial distribution? The events are all independent. You classify the outcomes as success or failure. And the probability of success for every single outcome is the same. In this case, it's 0.6. Okay, so the question might be, in this example, or in general, how do we figure this out? Is there a formula for this? What's the formula? And so let's talk about that. So let's suppose I consider this example. If I'm getting 5 heads, what could happen? Remember, so what's happening in this problem? I'm tossing a coin 10 times. Suppose instead of 5 heads, because I don't want the numbers to be the same, let's suppose I wanted the probability of getting 4 heads. So we want to compute P of X equal 4. Well, if I toss a coin 10 times, if I get 4 heads, it means I get 4 heads and 6 tails, right? So one possible occurrence could be, for example, head, 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 and then I would get 6 tails. So what I'm really asking, and by the way, if this happened, the probability of getting ahead was a 0.6. Right, I got 6 tails and 4 heads. So if I got 4 heads followed by 6 tails, by independence, I would have gotten this product. So the question really is, how many committees, this is really a committee of 10, right? There are 10 items here. So how many committees of 4 heads can I get from here? Every one of those, the number of ways that could happen is 10, choose 4, right? That's the total number of ways I can get 4 heads and 6 tails, a committee of 6 and 4. And in each case, I would get 4 heads and 6 tails. So the probability that X equals K for a binomial distribution is nothing more than N choose K. Remember, K is the number of successes. P to the K. And Q, remember Q is the complement of N minus K. We end up with a very simple result. This is the total number of ways you can get K successes from N. Simple combination. And we solve the problem. Where am I? So this is the probability of exactly K successes in a binomial distribution in a binomial distribution with success P, success probability P. So we have a binomial distribution. By the way, a very, very special case of a binomial distribution is when n equals 1. You only do the experiment 1. That's called the Bernoulli distribution. I'll just mention that in passing. So suppose I take the same problem now. I say determine the probability of at least 7 successes if a fair coin is tossed 10 times. So now n is 10. It's a fair coin, so the probability of success is a half. And the question is, what's the probability of at least 7 successes? That would be the probability of 7 plus 8 plus 9 plus 10. And now if each of these, you get 7 successes, from 10, choose 7, 0.5 to the 7, 0.5 to the 3, plus 10, 8, 0.5 to the 8, and 0.5 to the 2. Notice the power is always going to end up being 10 here because it's 0.5 plus 10, choose 9. 0.5 to the 9, 0.5 to the 1, plus 10, choose 10, 0.5 to the 10, and 0.5 to the 0 power, which of course is 1. We've got a calculator, and this will give you the answer. Now, which one do I want to use next? You should remember, by the way, that the sum of all the probabilities have to be 1. Remember that when we look at a plus b to the n, this is equal to the summation and choose k, the binomial expansion. Remember this? A to the k, b to the n minus k. K goes from 0 to n. This is important if you want to prove that the sum of all the probabilities of the binomial distribution add up to 1. And I worked that out for you as well. Okay, so there's a key question here. How's my time doing? Okay. So we have the binomial distribution. We know for the binomial distribution, the probability that x equals to k is the summation, excuse me, and choose k, p to the k. I'm sorry, that's not right. Oh, wait a second. Is and choose k, p to the k, q to the n minus k. So let's suppose you actually wanted to find the mean. Well, according to the definition, what you could do, it would be a mess. You'd have to sum this up. And ultimately, this would give you an answer. And that would be a lot of work. So what we want to do is we like to do this a couple of different ways. So our aim is the following. Mean and variance of the binomial. So there's a very clever way of doing it. We can also derive the moment generating function for this as well. I think I did this in the text for you. Yeah, so why don't I do that first? So the moment generating function, remember, is equal to e to the tx. So for the binomial distribution, this will be summation e to the t, well, x becomes k in this case. N choose k, p to the k, q to the n minus k, k goes from 0 to n. So this is one way of finding the moment generating function. Now let's rewrite this. I'll put the n choose k here. I'll take how do I do this? Let's say p e to the t k q to the n minus k. So I've just rewritten this expression. Now remember a minute ago, I showed you that a plus b to the n is equal to n choose k oops, what happened there? A to the k, b to the n minus k. K goes from 0 to n. So now, identify this with A and this with B. So this gives me, okay, so I'm going to replace A with P e to the t. And B becomes just Q. So I've just proven to the end. So I've just proven that the moment generating function is the moment generating function for the binomial distribution. I'm going to get this another way for you the next time, by the way. So for example, the derivative of this, bring down the power, decrease the power by 1. multiply times the derivative of the inside. And if I evaluate this at 0, when t is equal to 0, okay, and this gives me what? P plus Q is 1, n times P. So I've just proven that E of X is equal to n times P for the binomial distribution. I leave as an exercise for you to take the second derivative and then show for the binomial distribution. I'm going to do it another way very shortly, that the variance turns out to be n times P times Q, which is a pretty important result. Do I put that somewhere here? I'll do that later. Okay, so now observe. Let's summarize. Binomial distribution. P of X equal K. Is then choose K. P to the K. Q to the N minus K. It's P e to the T plus Q. The N is its moment generating function. E of X equals NP, and V of X equals NPQ. Now I want to do this one more time. That's my time first. Okay. I want to talk a little bit more about binomial distribution. Notice X is the total number of successes, right? So if I could define a X of I to be 1 if there's a success, and 0 if there's a failure. Then the total number of successes the total number of times I get a 1 is the number of successes, and that would give me X. So X is another way of looking at the binomial distribution, is breaking it up into n individual experiments. On each experiment, either I have success or failure, right? And each of these is the same. Each X of I is independent and has probability of success P. So E of X is just equal to the sum of all of these, which gives me the same number n times. But we know for a random variable of this type, E of X of I is equal to P. So E of X gives us the same results as before, NP. Similarly, V of X for an indicator random variable will be the sum of all of them. But we know V of X of I, they're all independent, is equal to, what does V of X of I turn out to be? Well, we know E of X of I is PQ, is PQ. So we get this n times so for a binomial distribution, it's almost intuitive. What do I mean? Let's suppose you toss a coin 100 times, and the probability of getting ahead is 0.6 on each shot. On the average, if you toss it 100 times, and the probability of getting ahead is 0.6, on average you would get 60 heads, n times p. Okay, so where am I? So let me show you what's happening. The first distribution I just considered is the binomial distribution. After the binomial, I'm going to consider hypergeometric and geometric and negative binomial. And then the Pascal, and then the Poisson. That's basically this last section. Right now, I just want you to do homework exercises on the binomial, which in section 2.12 I didn't go beyond. I wouldn't go beyond problem number 13 in section 2.12 right now. Okay, so let's assign those problems. And of course, the problem in 2.11. And what we'll do is we'll come back on Monday. We'll go over some of these problems involving the binomial distribution. I know some of them are going to bother you. But again, the key part here is how to find the probability for the binomial distribution. Okay, it's a moment generating function. It's mean and its variance. We're going to do the same kind of analysis for the other distributions as well. Anybody have any particular questions? Any questions, anybody? Again, I told you about the exam. I hope you grade your exams over the weekend. I hadn't had a chance to look at them yet because I've been ill. I am quickly recovering. I'm still a bit tired. I guess you can hear it in my voice. But go over these problems. Come in with questions on Monday. We'll work out some examples on the binomial distribution. Hopefully by then I'll have your exam completely worked out. Anybody have any particular questions? All right, let me stop the recording.